if you go through the next 15 minutes, 10 minutes maybe, I'll guarantee that you'll have a far better understanding of where the square root 3 and 30 degrees are coming from in a delta network. Okay, so it is always a good idea to start from the sketch of what a delta configuration looks like. So a three-phase system at the end of the day is essentially your three single phases, right? Let us just ignore everything else and look at this particular voltage source as a single phase generator. Make sense? Okay. Which is connected between terminals A and B. Okay. Why small a? Why small b? The reason is that we're looking at a source. Okay. So the voltage between this point and this point is simply VAB. Okay. Now the current that is generated by this single phase generator, if the voltage is VAB, I can call the current as IAB. This is a key point. Why? Because when you see this, it is a common mistake that students make. They interpret for a delta configuration IAB as something called a line-to-line current. There is no such thing as a line-to-line current, right? There is only line current and phase current. Okay. And the reason for that confusion is that VAB is line-to-line voltage. Okay. So the thought process is that IAB must be a line-to-line current. It is the phase current for a delta configuration. I'm taking baby steps over here because these are the areas where mistakes are made and points are lost. On the FE Electrical and Computer exam, one question is worth 1 divided by 110, and I'm not going to assume, I'm not going to get into that whole discussion about 10 questions are not counted. You don't know which 10 questions are experimental. Or let's just keep it simple, 1 divided by 100. So that's basically 1%. One incorrect question costs you 1%. If we are looking at P power 1 out of 80, one question costs you 1.25% of the total score. It's higher weightage. Okay. And just by making a silly mistake, which seems silly, but it's a conceptual gap, to be quite honest, something like this, you are leaving points on the table, money on the table. Okay. All right. So we are clear about a single phase generator, which is connected between two terminals that I'm calling as A and B, like this. Now for a delta configuration, what we do is that we complete a loop. I'm going to pick another generator, another source of voltage. This is AC, as indicated by this sinusoidal sign in between. If I remove it, it would imply DC. But it basically completes a loop in terms of head to tail. The positive terminal of this guy is connected to the negative terminal of this one. The positive terminal over here is connected to the negative, and the positive and negative, and so on. Okay. So this one is connected between, this terminal is C, right? So this point is C and this point is A. So this becomes VCA, and the current that is pumped by this particular generator is ICA, and then IBC, and so on. Starting from the configuration, starting from the labeling of voltages and current is extremely important. Because if we don't do that, we are not going to really understand where the square root 3 and 30 degrees is coming from. And that is the ultimate goal of this session. I want you guys to understand where is this square root 3 and 30 degrees coming from and how can we handle it. Now, let us assume that the first generator that we installed between terminals A and B of this delta configuration is my reference generator. Okay, reference in the sense that its voltage will be considered, first of all the voltages are equal in magnitude, but as far as a phase angle is considered, I'm going to assign it 0-degree phase angle. Okay, then the next one is going to be VBC. So this is going to be lagging behind 120 degrees, and VCA is going to be lagging behind another 120 degrees. So that basically becomes VAB, VBC, and VCA. And all three of them have the identical magnitude. Okay. So that's the story with the voltages. Now, the interesting thing is that just by looking at this configuration, you can unlock the voltages right away without lifting the pen, doing any type of calculations. Why? Because if you tell me the value of VAB in a delta configuration, which by the way, as you can see, is a phase quantity, right? In delta, as you can see, the line to line voltage, the voltage that is appearing between here and here, and the voltage that is across the terminals of the generator are basically the same voltages. Okay. In delta network, our problem, our issue, our headache is not the voltages. Our headache are the currents. Okay, and I'll explain you why. So what we see over here is that VAB is equal to this, VBC is equal to this, VC is equal to this. So you only need to be told about VAB, okay, and then you can basically rotate the others by 120 degrees and you will be able to unlock VBC and VCA. Very easy. Now I can go in a little bit more detail in another session. I've basically captured why VAB and then why BC and then why CA. I'll just take a quick minute to explain you. That's because inherently we are dealing with an ABC network, ABC sequence. Okay. So ABC basically means that you have phase A, okay, then a 20-degree phase shift with phase B, and then 120-degree phase shift with phase C. So these are all 120, but this is a counterclockwise movement. So we start with A, and then B ends up at the positive x-axis, and then C ends up at the positive x-axis. So whenever we are calculating the line-to-line voltages, right? So this basically means that it will be VA minus VB. Okay, the delta between them, the difference between them is going to be the first voltage that is appearing and then the second voltage that's appearing. So this is only going to result in VAB. And then if I am calculating the difference in the line-to-line voltage between phase B and phase B appears first, and then phase C appears. So this basically becomes VB minus VC, which is VBC. Okay, and guess which phase is going to appear next? This is going to be ABC again. And now when we are establishing a relationship between line-to-line voltages of our phase C and phase A, or phase A and phase C, it has to be VC minus VA, that's VCA. So the reason that I gave VAB a 0-degree reference, as you can see over here, is because it relates to the ABC sequence. In ABC sequence, we have VAB, we have VBC, and VCA only. Okay, so this is the level of detail and the nuances that you have to appreciate in order to fully understand these configurations. Okay, so the voltages are fairly easy to understand. They, depending on the phase sequence, okay, they just have to be rotated by 120 degrees. And let's say if instead of VAB, if I had VBA, then that indicates a negative sequence, and an entire discussion on the negative sequence ACB configuration. We can spend half an hour just on that. Okay, I want to focus on the current. That's where the square root 3 and 30 degrees is going to pop up. You don't see any square root 3 and 30 degrees jumping out of the voltages. Life is fairly good, right? When it comes to voltages, they are just simple 120-degree phase shifts and the equal magnitudes. But that is not the case with the current. If I do a simple KCL at this particular point, for example, I see that the current IAB is entering this point. Okay, let's just call this point X, right? At point X, at node X, which is basically our terminal A, we have IAB that is entering and ICA and IA is leaving. So without any understanding of power systems engineering, just knowing the fundamentals of circuit analysis, knowing the fundamentals of KCL at point X, I can write a KCL that will say that IA enters the node, IAB enters the node, and it splits into IA plus ICA. Okay, I don't think anybody is going to disagree with me, right? Simple, straightforward. Now, I am going to assume that we have understanding, and I'll explain you why that is a fair assumption. We have the knowledge of our currents, IAB and ICA. So we do know what is happening with the phase currents. They are phase currents because they are being pumped out by these generators that are connected on each phase, right? In a delta configuration. So I'm basically dealing with an unknown, which is this guy. Okay. I'm going to rearrange the equation and I'm going to say that my IA is equal to IAB minus ICA. Okay. So far, so good. Now, assuming that, so remember our voltage and current relationship, according to good old Ohm's law, is fairly simple. Voltage is directly proportional to current, or current is directly proportional to voltage. When you include an equality sign, you have to introduce a constant. If you're dealing with a purely um, real load, resistive load, it just simply becomes I. If you're dealing with impedance and that contains also reactive component, then basically it's equal to Z. Let us assume that we are dealing with a simple real load. Then that basically means that my V is equal to IR would basically mean that my current, and please pay attention to this, it's an important concept. The current is equal to V divided by R. Now, from a mathematical standpoint, what is the significance? Let me explain you. If the current is equal to voltage carrying a particular phase angle, let's just call it a phase angle of V, which is being divided by current, which carries a particular phase angle, let's call it theta R, right? Now, the interesting fact is that resistance is a simple scalar quantity always having a phase angle of 0. Okay, so this I can replace at 0 degrees. So that basically tells me that my current, okay, is simply a scaled version of my voltage, such that the angle theta for the current is always equal to the angle theta of the voltage. Now, this has implications, right? Why does this have implications? Because what we're going to do over here for IAB is that we are going to simply import the phase angle of VAB, which is 0 degrees. What I'm going to do with ICA, okay, is simply to import the phase angle of VCA. Now remember, these derivations may seem like a waste of time at the moment, and you might be thinking, I have all the equations in the P Power Reference Handbook, in the F Electrical and Computer Reference Handbook. I don't know why Wasim is wasting my time, and I don't know why I'm attending this session, right? But here's the kicker. These equations are not in the reference handbook. They're not in the reference handbook for P power or FE electrical specifically for the Delta network. And this is one of the main reasons why Delta configuration is so difficult to deal with. Okay. So it's important to go through them at least once. And you cannot assume that everything that I'm going to be tested on is just going to be very nice, simple, straightforward, walk in the park Y configuration. Okay. All right. So minus 240, because of this reason, I can import, right? So let's see where this goes. Assuming that we have a balanced system, as I mentioned, is the one where the magnitude of the current on phase A, phase B, phase C, the line currents, the phase currents are all equal. And the only difference is that they're 120 degree apart, right? So if that is the case and we're dealing with the balanced system with balanced loads, as far as the magnitudes are concerned, we can just call them phase values, right, for the current. And what we are left with are just the phase angles over here. Okay. And now you can see that things are starting to make sense. Why? Because now I'm just going to do complex mathematical calculations, not difficult complex in that sense. It's just rectangular and polar. And that will basically unlock the relationship between line, and notice this, IA, if I blindfold you and you're like, I'm just going to ask you rapid fire questions. IA is line current or IA is phase current? If you are extrapolating your understanding of voltages and going back in time and VA is phase voltage over here, right? VA is phase voltage over here. So IA must be the phase current. Wrong. Because IA is the line current. Okay. So the connection that now we are making is between the phase currents, right? And the line current. And all we got to do is simple math. Okay. So I explained to you how we set up IA is equal to IAB minus ICA, right? This is 0 degrees because we are simply carrying our phase angle from phase AB, VAB phase voltage, right? And then this is for CA, okay? Now, what I would like you to do at least once, remember, if you go through this exercise once, you're going to be fine, right? Let's do a cosine of 0 degrees because I phase 0 degrees is equal to I phase cosine of 0 degrees plus j I phase sine of 0 degrees, correct? So sine of 0 degrees is 0. This is gonna just leave me with I phase of 1, okay, which simply is I phase. All right, so this is how I'm able to reduce this into simple I phase. Now, if I go through the same exercise for my I phase 240, minus 240 to be precise, I phase minus 240, right? And this is simply using our polar form. This formula is given in the reference handbook, R cosine theta plus JR sine theta. No rocket science here, okay? This is I phase cosine minus 240 plus JI phase sine of minus 240 degrees. If you punch this in your calculator, guys, you're going to see that cosine minus 240 degrees is going to be minus half, and sine of minus 240 degree is going to be square root 3 by 2. Okay. And both of them are being multiplied by I phase. Both of them are being multiplied by I phase. And this is how I end up with this in the brackets. Okay. Now this is leading us somewhere. This is leading us somewhere. What we are going to do now is that we've basically arrived, and it requires patience, attention, and focus. We've arrived at this. And please don't just watch me do this. I want you, in fact, I'm going to give you homework. I did phase A. I would like you to start from KCL, okay, after you finish this session, and actually do the same thing on phase B, do the same thing on phase C. You'll get 2 more shots at really understanding this inside out, okay? So what I'm doing over here, if I open this bracket, can you guys see that this negative multiplied by this negative is going to turn into a positive, and you'll have a I phase plus a half of I phase that results in 1.5 I phase, correct? Or 3 by 2 I phase. This negative sign is going to multiply inside with this guy, right? And you are ending up with minus j square root 3 divided by 2 I phase. Make sense? Okay. Now the final move is extraction of I phase, which is common in both of them, and square root 3, which is common in both terms. If you're wondering as to where is the square root 3 over here, Wasim, so this is I phase 3 by 2. This is actually square root 3 multiplied by square root 3 by 2. Hopefully it's obvious to all of you, okay? Because this is simply 3 raised to power half, 3 raised to power half. Square root is basically half, right? And that basically the powers add up, so you get that. So when I pull this out, something really interesting happens, okay? I am left with this factor, square root 3 divided by 2 minus j times half, okay? And this is where the final piece of magic happens, okay? There's been magic. Hopefully you are able to see magic happening throughout the session. Okay, the final piece of magic is right here. I can actually compress this, consolidate it, okay, and capture it as a phase angle of minus 30. And you're like, no, this is cheating. How do you do that, right? Well, it's pretty simple. If I do a cosine of minus 30 plus a j sine of minus 30, do I end up with anything other than square root 3 divided by 2 minus j by 2? No, I don't, right? So this is square root 3 by 2, and this is plus j, but minus half. So that basically results in that. Make sense? Okay, now this is basically what we had been working for, right? Square root 3 and 30 degrees. After going through all of these steps, right? Number crunching and mind numbing calculations, they're not that difficult to be honest, but what we were after, we couldn't find in terms of voltages, but we were hunting down square root 3 and 30 degrees. And let's see, we already have that over here. Okay. On the left hand side, I want to remind you what we had been carrying throughout this IA. In other words, a line current. Let's see how that line current looks like. So the big find is that in a delta network, and you will not find this in the reference handbook for P power or FE electrical. In a delta network, we have the line current equal to the square root of the phase current's magnitude. Okay. This is still not the most difficult part to remember, because in a Y configuration, I'll tell you this, the line voltage is equal to square root 3 the phase voltage. So you can just extrapolate that from there. You'd be like, okay, delta network deals with current. Current is a pain in the neck in delta network. So I'm just going to remember, or it's already given to me in the reference handbook for Y network. So I'm just going to switch out the voltage with the current. I'll be done, right? Yeah, I think that's good enough if you're dealing with just the magnitudes. But here's a kicker. In our Y configuration, the relationship between the line voltage and the phase voltage is such that square root 3 V phase magnitude, fine. Angle is 30 degrees. In other words, your line voltage leads the phase voltage by 30 degrees. Over here, what ends up happening is that instead of plus 30, you have a negative 30. Okay? That basically means that your phase angle for the line current is going to be lagging behind the phase current by 30 degrees. And what are the implications? Let us assume that our phase A is VAB was a reference, right? So it was 0 degrees. Okay. So this is our phase AB, right? The first one that relates to IA. This is going to be 0 minus 30 degrees. Okay. And that's how it ends up being minus 30. So for B, we were at minus 20. So minus 120, sorry, pulled back by another 30 degrees results in 150. And then minus 240 minus 30 is going to result in minus 270 degrees. Okay. So this is where the square root 3 and 30 degrees come from in the delta network. It is not intuitive. It is not given in the reference handbook. It requires attention to detail. Even if you want to kind of cram this formula, you have to be careful in terms of handling the phase angle. You have to be careful in replacing the voltage with the current. And I am okay with you developing a strategy in order to memorize this formula, fine, but that should not come at the expense of just short circuiting all of these fine details. At least once you should go through them. In fact, a homework assignment that I will leave you with is to rinse and repeat the same process, all the calculations, carefully work through the phase angles, the subtractions, the additions, and conversion from polar form to rectangular form, and so on and so forth, and back to polar form with B and C, just like I did for A. Okay. So hopefully by going through this session, at this point, you have a better appreciation and understanding of the nuances that are involved with the delta network and why the delta network is more challenging than the Y configuration. Two reasons: you cannot apply the Ohm's law directly. And the other reason is that in the context of FE electrical and computer exam preparation, in the context of the PE Power exam preparation, where you have more than 100 equations provided to you in the reference handbook, this particular equation that spells out the relationship between the line voltage, the line current, and the phase current and the phase voltage for delta network is completely missing. Okay, you have a better chance of understanding and tackling the questions related to delta network once you've gone through a detailed derivation like this. Okay, so I hope that you can see the benefit of having a structured approach, first principle based approach, level 3 understanding, not skipping any steps, going through all the details step by step. And delta network is a mystery for a lot of power systems engineers. And in the last few minutes, we basically gone through the three-phase system, the delta configuration, the derivations, and all the fine details related to a very important concept that applies to both FE electrical and P power. And if you just extrapolate this and imagine working through every single concept for the FE electrical and computer exam preparation, as well as the P power exam preparation in a stepwise manner, and not only just the explanations within my FE electrical and computer exam preparation program, you can find details on my website, studyforfe.com. Every single topic is broken down into conceptual pieces, granular pieces that you can understand, followed up by high quality practice problems with a lot of details, stepwise explanations. You will essentially be in a far better position to take on these exams with confidence. And time is of essence, essentially. You can find details, do your research, free resources, ChatGPT, Google. There is no shortage of information, at least in this current age, right? So you can always find answers to the questions that are bothering you. But the question is how much of friction and overhead you're going to experience. With my program, it's essentially a one-stop shop with a lot of support structure around it. I have a community, an exclusive community for my students where they can ask any technical questions. I assist them with all the responses. My teaching assistants help them with all the responses. In a very structured manner, you will always be getting answers to your questions in a very short period of time. And they are computer simulated practice exams. So at the end of the day, if you have enough commitment, enough passion, enough incentive, any journey can be completed, right? A journey which is not laid out properly can potentially look like this. But if you use a structured approach, it can be a little bit more easier and, dare I say, a little bit more fun to go through as well. So feel free to check out my exam preparation resources for both FE electrical and computer exam as well as P power exam at my website, studyforfe.com. If you want to just do a monthly subscription, the monthly subscription is available. You'll get access to the on-demand course. If you go with the on-demand plus live training bundles, then you will also have weekly live training on top of the on-demand course. And then also master classes, which are essentially crash courses on every single topic. And both FE electrical and P power programs contain upwards of 1,000 practice problems in the coursework, combined with the computer simulated practice exams that mimic exact exam-like conditions in terms of the timer and everything, diagnostics, flagging, going back and forth between the questions, the navigation, and the whole 9 yards. Okay. If you're new to this channel, please consider subscribing. On a weekly basis, I'm creating content for FE electrical and P power exam preparation. I also discuss topics related to electrical engineering with a focus on power systems engineering. If you'd like to learn more about my FE electrical and P power exam preparation programs, please visit my website, studyforfe.com.